Okay, guys, so we're starting today on the next part of Unit 1.2, and this is simplifying non-perfect radicals. I think the instructions are, the name of it is radicals. What did I name it at the bottom? Simplifying radicals. Okay, so there's your objective. I will be able to simplify non-perfect radicals, in other words, roots, and combine like radicals. And I'll take that off of freeze so that you can see what I see. Okay, so I'll give you a second to write that down. And typically when I get students of your caliber, most of you have been exposed to it, but not had a lot of practice. And so hopefully today is not your first exposure. If it is, if I have to work a little harder, but definitely capable of doing it. So let's talk about what a radical is. A radical, we call that a radical sign. Okay, and I'm just going to talk about radical expression in all of its parts. So we call the number that goes in the groove of our radical sign an index. It's called an index. Okay. We call the number that is under the radical sign the radicand. And of course, this is a radical sign. And together they create a radical, or a radical expression, if I want to be really particular about it. Hopefully that's not your first exposure to all of the parts of a radical. Okay, so there's a radical. And we're going to be combining like radicals. What I'm going to do is I'm going to give you some examples of like radicals so that we can identify them when we're working on our assignment today. So an example of like radicals could be this. 3 square root of 2 and negative 5 square root of 2. We would consider those like radicals, similar to like terms. If I have like radicals, I can add them. I can subtract them. They are like radicals. So what makes them like is that these are exactly the same. The coefficients out front can be different, but the radicals must be the same. However, we do have to take into consideration that some of these problems that we'll be working on today will have variables, and as we know, like terms will have like variables. So here is another example. Oh, probably yellow is not a good color. Let me change here. 3x to the cubed root of 2x, and somebody give me an example of a like radical that I could write that would go with this. Anybody? Actually, that wouldn't quite be there. You're close, but the reason that that would be wrong is that you're not identifying that variable. So you want to use negative 5. In order for these to be like radicals, the variables have to match exactly inside and out. Oh, okay. Gotcha. Okay. So in order for these to be like radicals, they have to match
after the coefficient, and that should be an x there. It just didn't want to write for me.
Okay, so they have to match after the coefficient. Okay, your variables have to match all the way across in order for me to combine those radicals and for them to be considered like.
Does that make sense? Yes? Okay, so I don't want to write a verbal explanation of like radicals. I believe that is a great visual for like radicals for you. Okay, so let's go and look at the next page or the next part now that we've talked about our vocabulary terms. It's these rules here, these properties of radicals that you've been provided. Okay, the first rule is the multiplication, and I keep calling it a rule, it's a property. The multiplication property of radicals says that if I'm multiplying two radicals separately, I can put their radicands together and multiply them. Now, why is that important to note? So it's important to know that sometimes it's better to have separate to separate your radicands, and sometimes it's better to put them together. For example, if I were to say the square root of 2, you can just write this. I gave you a little room. You probably could fit it in there. Times the square root of 8. Okay? Now, I could work at that problem in the form that it is, but it's probably going to take me a little longer. In this situation, it would be better for me to do what? What do you think? Can't I multiply them? Isn't this the same thing as the square root of 16? Can you see that? I just put them together. 2 times 8 is 16. Which one's easier to see the answer for immediately? 16. This equals 4 immediately. Whereas over here, if I left them separated, I have the square root of 2 times 2 square roots of 2 if I simplify the square root of 8, so I have to know how to do that. And so I would remultiply that to have 2 times the square root of 2 times the square root of 2, which is 2 square roots of 4, which is 2 times 2, which is 4, and it's a lot of work. It's a lot of work. So the purpose of having this property is so that we can make choices. Do we want to put our radicands to multiply them together? Will that make this problem simpler to solve, or do we want to take them apart? For example, if I give you the square root of 50. Well, we know that's not a perfect square. We can do a couple of things here. But would it be easier to look at if we were to separate this into 2 square roots? What's a really big perfect square in 50? 25 times what? Times 2. So this is just going from this form to that form, and the square root of 25 is 5 square roots of 2. So this is just a multiplication property for radicals. Sometimes it's better to put them together. Sometimes it's better to pull them apart. And the same goes for division. So for example, if I were to give you this problem, the square root of 90 over the square root of 10. Now, there's 2 ways I could go about solving that. Would it be better for me to sit here and rationalize my denominator or put them under the same square root? That's not 100, that's a 10. What's the answer to 90 divided by 10? 9. And what's the square root of 9? Versus if I were to go and tackle the other problem in its format, I'm going to erase some things so I can just show you real quick. And I'm doing this because I want you to understand the power of having the decision. You can make the decision. So if I was to take the square root of 90 and the square root of 10, and I wanted to simplify that in this form, I would have to multiply it times the square root of 10 over the square root of 10, which equals 1, which will give me the square root of 900 over 10. And the square root of 900 is 30, and 30 divided by 10 is 3. Same answer that I got the first time. But look at all the work that I had to do to get there. So again, I hope I've emphasized it enough. Excuse me. You have to stop and analyze the problem and make a decision. What should I do before I begin? Okay, be careful. These combinations don't work for addition or subtraction. Fill in the blanks. They do not work for addition or subtraction. These combinations only work for multiplication and division. Also, there's a typo on your paper. You'll notice it in this first part. Mine doesn't have a typo, where it says the square root of 9 plus 4 does not equal, and I didn't separate them. I need you to cross out that second square root of 9 plus 4 and change it to the square root of 9 plus the square root of 4. Okay, because and you can see that it's not true if we sit here and simplify. The square root of 9 plus 4 is the square root of 13, which is not a nice, beautiful, perfect square. And over here, we would do the square root of 9 is 3, plus the square root of 4 is 2. So basically, we're saying that the square root of 13 does not equal 5. Therefore, we cannot apply this combination property for addition. And it also does not work for subtraction. Same line. So just remember to be careful. It's a common misconception. If I don't point that out, that's a common misconception. We don't want that to happen. Okay. Questions before we move on? All right, here we go. Next. The next instructions say simplify these non-perfect radicals. Okay? These are not perfect squares or perfect cubes or perfect fifth powers, whatever I have of them. Okay? But you're asked to simplify them and write them in exact form. So when I look at 12x to the fifth, the square root of 12x to the fifth, I'm thinking 12 is not one of those really nice numbers in that form. But I could apply that multiplication property and tell me what is the biggest perfect square in the factors of 12. 4? Would you agree? So the square root of 4, I'm going to leave a little space for my x, times the square root of 3. So I'm going to separate them using my multiplication property. Okay. And then I'm also going to attack my my variable there. That's x to the fifth. And this is a square root. And so I'm wondering how I can pull a perfect square out of x to the fifth. And the answer to that is I'm just going to separate x to the fourth, which is a perfect square. It's the largest perfect square I can get out of x to the fifth. And I will have how many left over? Here. And so what I did was I put my perfect squares in the first group, and I put my non-perfects in the second group. And now I'm going to simplify. So this is 2x squared, because how many squares can I get out of 4 x's? I can get 2, right? 2x squared square root of 3x. And that is the simplified exact version of that original fraction. Something that you can do with exponents, like for example, if you're wondering how I got to x squared, if I were to do this, the fourth root of 2 to the 8th power, and I'm just going to leave it in that format. What would my answer be? I would ask you, how many times can I group this in 4s? Twice. So the answer would be 2 squared or 4. Can you see another combination? Now what I'm talking about is I'm talking about it properly, but could maybe you see a quicker way to get to 2 squared as an answer? What am I doing with those exponents, really? What did I do with these 2 exponents here that I did with these 2 exponents here? I did divide them. This is 4 divided by 2 is 2. This is 8 divided by 4 is 2. So I did divide them. And so that's an exponent for radicals. All right, let's take a look at the other one. Good job, Dallas. Good eye. All right, let's take a look at this next one. Now, this next one has got a really big value. And it's a cubed root. Okay, so finding the perfect cube in 432 is probably not something most people can do. So when I come to problems like this, I will fall back on a factor tree to help me find the perfect cube in 432. So what I do is I'll take 432 and I'll start breaking it down in a factor tree. And if you birthday cake it up, whatever, that's the way you were taught to do that, that's fine. Let's start by cutting it in 2. 2 goes into 4. I'm just going to divide this way twice. 2 goes into 3 once with 1 left over, and 2 goes into 12 16 times. Now, if I had my little perfect my power page out, I might see that 216 is a perfect cube. It's 6 cubed. It is. It's 6 cubed. So at this point, if you had that out and you were looking for it, you could stop there because it's a perfect cube. However, you might not. You might continue to cut it in half. Half of 216, would you agree, is 108? And half of 108 is 54? Yes? And half of 54 is 27. And now I can't cut in half anymore, so I start cutting in 3 times 9 and 3 times 3. So I may have just decided I'd rather just finish factoring this out than look through my perfect cubes to find 216. So what I'm going to do is I'm going to circle my cubes. Here I have 3 cubed. Yes? And here I have 2 cubed. And then here I have this leftover non-perfect cube right here. Okay? So I'm going to come over here and put my perfect cubes in. And I'm going to just go ahead and leave them as cubes. So that's 2 cubed times 3 cubed, right? And over here, I'm going to have my cubed root of 2, which was my leftover cube, or my leftover factor. Okay, so now I've got my numbers taken care of. Now I'm going to go look at my exponents on my variables. So how many groups of 3 can I make out of 9? Right? Can I make 3? Right? Will I have any leftover x's to put over here? No. How about my y's? Can I get a cubed root of y's? No, so I'm going to put that over there. Okay. So now I've separated my cubes from my non-cubes, and we're going to finish this out. So you know that cubes and cubed roots cancel each other out, or what's 3 divided by 3, and 3 divided by 3, and 9 divided by 3, so x cubed, and then a leftover cubed root of 2y. And then remember I told you that 216 was cubed root of 6, so our final answer is 6x cubed, cubed root of 2y. You won't see many like that where the numbers are the type that you would have to rely
on your factor tree to help you find your perfect cubes or fourth powers or whatever you're being asked for. Most of the numbers are a lot more manageable than that. I think I gave you one or two where you're going to have to really rely on a factor tree to probably get it down to the correct answer. Most of them will be more similar to the first example. Okay? Questions about that? So that's simplifying radicals. And once I know for sure you can do that on your own with your own power and your own brain, I'll let you start relying on the calculator to get there faster. Just want to know that you can do it first before you use the calculator. Moving on. Ready? So now we're going to start simplifying some addition and subtraction problems. So we're going to be trying to combine like radicals. So our next problem is here. We have three different problems to look at. The first one is 3x square root of 2 plus 2x square root of 2. And I have to simplify them. So my question to you is this: are they like radicals? Yes, and we know that because they both end exactly the same after the lead coefficient. So I would use my factoring skills to say that these have a common factor of x square root of 2. So I would write this at factoring out the x square root of 2 as 3 plus 2 quantity x square root of 2. And I'm using my factoring skills. Now typically when I factor, I'll take the common factor and throw it out in front of the parentheses. But in this situation, radicals pretty much always get tagged on the end. So I'm going factoring it out, my common factor, on the back end of the parentheses, finishing that out. That is 5x square root of 2. And I'm sure that a lot of you can see that without the factoring step, and that's okay. But for note purposes, I'm always going to factor. Okay? Factoring, excuse me. Factoring is coming up soon, so I'm just bringing it back now. Let's look at the next one. Are they like radicals? But what if I simplify them? Is it possible that they could be? We need to simplify each one to know. So let's take 27, and this is the square root. So what's the biggest perfect square in 27 using our multiplication property? Square root of 9 times the square root of 3, right? And what about 12? Biggest perfect square? Square root of 4 times the square root of 3. Guess what those are? Like radicals. 9 square root, this is 3 square roots of 3 minus 2 square roots of 3. They are like radicals. So I'm going to factor out a square root of 3. So I get quantity 3 minus 2, square root of 3, subtracting my lead coefficient there. And that would be 1 square root of 3. However, I wouldn't write the 1 because you can see that there's 1 square root of 3 right there. So putting a 1 in front of it is redundant. Questions about that? Okay. So there was a little hint in this problem once I got to right here that indicated that that was probably going to be my like radical on the other side. You're going to find that that happens again right now. So these are not like radicals on C in the form that they are. But let's go ahead and take 50 and apply our multiplication property. What is the biggest perfect square in 50? 25 times the square root of 2. So what do you think this last little common square root is going to be? No, 25 is a perfect square. It's going to be square root of 2. So we're going to have minus 3 times, well, what times 2? Biggest perfect square in 200 is 100 times the square root of 2. So that non-perfect square is now matching, and we're going to go ahead and just figure this out. So this becomes 2 times 5, square root of 2, minus 3 times 10, square root of 2.
or 10 square root of 2 minus 30 square root of 2. Factoring out their like radical, I have 10 minus 30 times the square root of 2. Then, of course, combining my coefficients here, I get negative 20 square root of 2. So I was able to simplify that problem by trying to identify like radicals. Okay, we have 2 more examples that we're going to do together. And D is probably the most complicated of all of them. So D, here we have D. And these are fifth roots. And when I look at D, before I even start breaking it down, I try to see if I can find out what the like radicals are going to be. So I'm looking at the fifth root of 64z and the fifth root of 2z to the 6th. Well, 2 doesn't have a fifth root, right? Right? So I know I'm probably going to have a 2 left over here. That's likely. And then over here I have a z to the 6th, which does have a perfect fifth. And this one, z to the 1st, so it doesn't have a perfect fifth. So what do you think my leftover non-perfect root is going to be? What from here can't I break down? The 2. What from here can't I break down? So I'm guessing that my leftover non-perfect radical is going to be the fifth root of 2z. I'm thinking that. So when I'm looking at 64, I'm thinking, what could I do to separate a 2 out of that? What times 2 is 64? 32. And isn't 32 a perfect fifth? Isn't 2 to the 5th 32? So a fifth root. And then, of course, we would have to multiply that times the fifth root of 2z, because the only perfect fifth root in 64 is 32. And on the other side, we have 2. And let's talk about where's a perfect fifth in 2z to the 6th. It's a fifth root. Can't I get 5 z's out of that? Can I write this as z to the 5th times the fifth root of 2z to the 1st? So I pulled a perfect fifth power out of z to the 6th. I can do that. Okay, let's simplify. This is 3z times 2, fifth root of 2z, minus 2. What do I do when I do the fifth root of z to the 5th? They cancel each other out. It's just z, fifth root of 2z. Got it? Are they like radicals? We're going to go ahead and put these two together. You guys agree that that's 6z? Fifth root of 2z minus 2z, fifth root of 2z. Definitely like radicals. After the coefficient, they match exactly. So we would factor out a what? Do you guys know what I'm saying when I'm saying factor it out? We're factoring out a z, fifth root of 2z, leaving us with 6 minus 2, which a final answer is 4z, fifth root of 2z. It's a lot of work. Thankfully, we won't have to do it very often. When we get to our quadratics a little bit, we'll have to go back and do some possibly. Or quadratic. Okay. So E. E, you have 2x square root of 3x minus 3 square root of 3x. So a question is,
Can I simplify the square root of 3x? No. Are they like radicals? Try again. After the coefficients, do they match exactly? No. This is an x square root of 3x, and this is just a square root of 3x. It is already simplified. They cannot be combined. That's the answer. It cannot be simplified because they are not like radicals. You just have to make yourself a little note to be careful. So what if I put that one on a test? I might, just to see if you're being careless or not. And that you really learned what you were supposed to learn. Okay, I'm going to give you the answers for the self-check so that you can get where you need to get by practicing and possibly working together. The answer to A, final, is the square root of 2. Might want to write that down so you have it. And the answer to B is 8a cubed root of 3a. So for homework, would like you to have your work done for that. And of course, it would also like you to write your self-reflection. Beyond that, on the same worksheet you were working on yesterday, we are going to continue with the assignment. I am assigning you 16 problems. And many of them are more like A, B, and C than they are like D and E. The homework is this: 63 to 93, 65 to 93, every other odd, and 66 to 94, every other even. So just start on 63, 65, do a pair, skip a pair, do a pair, skip a pair. And if you want to do them all, the other pairs are extra credit. Okay? So extra credit is the other odds and evens. So that would be a total, I think, of 30 problems, which is a lot when it comes to these. They're pretty tedious. So I didn't want to give you a whole bunch to do. Okay? And yesterday I handed back the test, right? The quizzes. You know that you have a new quiz on Friday, and you're having 2 quizzes on Friday. The other quiz will include the notes from stuff from yesterday and stuff from today, not the stuff from tomorrow. Okay? Okay. Thank you very much. Probably I could stop that video because holy moly.